Good morning students, welcome to video lecturing on basic second sem mathematics on the topic Jacobins. Today let us study on the functional dependence and independence. First let us take the definition of this one. Any two functions u and v of two independent variables x and y possessing the partial derivatives dou u by dou x, dou u by dou y, dou v by dou x and dou v by dou y, not all of them simultaneously 0, are said to be functionally dependent if there exists a relation phi of u comma v is equals to 0 such that phi is a differentiable function. Then we can say that here if phi is function of u and v and this one phi of u comma v is equals to 0 such that here u, v and w possesses the partial derivatives, then such function is known as such function is known as here functional dependence. Let us take one theorem here. Necessary condition of this function to be functionally dependent. If the functions u, v and w of three independent variables x, y and z are functionally dependent, then dou of u, v, w divided by dou of x, y, z is equals to 0, or Jacobin of u, v, w divided by x, y, z is equals to 0. Let us take the proof here. Since u, v and w are functions it is given here they are functionally dependent, then there exists a relation. So this is from the definition of a functional dependence function we have here. Then there exists a relation phi of u, v, w is equals to 0 among them such that phi is a differentiable function. That is here phi is a function of u, v, w and u, v, w are functions of x, y, z. And this implies here phi is a composite function of x, y, z. So therefore by chain rule we have here dou phi by dou x is equals to, here phi is function of u, v, w, after that u, v, w are functions of x, y, z. So phi of dou phi by dou x is equals to dou phi by dou u into dou u by dou x plus dou phi by dou v, dou u by dou x plus dou phi by dou w by dou x, and it is equals to 0 because here we know phi of u, v, w is equals to 0. We can take this one is equals to 0. Similarly, dou phi by dou y is equals to dou phi by dou u first because it is with respect to u, and u is again in terms of y here, then plus dou phi by dou v into dou v by dou y plus dou phi by dou w by dou y is equals to 0. Similarly, last variable dou phi by dou z is equals to dou phi by dou u into dou u by dou z plus dou phi by dou v into dou v by dou z plus dou phi by dou w into dou w by dou z. It is also equals to 0 because here because it is given that here phi of u, v, w is equals to 0. Therefore, we can take these are all equals to. This is a homogeneous system of equations. For the unknowns dou phi by dou u, dou phi by dou v and dou phi by dou w. So this system will have a non-zero solution only when the determinant of coefficients vanishes. That is determinant of here dou u by dou x, dou u by dou v by dou x, dou w by dou x. Second row is dou u by dou y, dou v by dou y, dou w by dou y. And third row is dou u by dou z, dou v by dou z, dou w by dou z is equals to 0. Let us interchanging these rows and columns. We know here interchanging rows and columns is nothing but transpose of a matrix. So if you make transpose, then there is no any change here. Therefore we can here transpose this, that is interchanging the rows and columns. Then we have here if you interchange rows and columns, this column becomes row, that is dou u by dou x, dou u by dou y, dou u by dou z. And second column becomes second row, dou v by dou x, dou v by dou y, dou v by dou z. And third column is dou w by dou x, dou w by dou y, dou w by dou z is equals to 0. This implies here we know this is the definition of a this is Jacobin of u, v, w with respect to x, y, z. That is dou of u, v, w divided by dou of x, y, z, and it is equals to 0. So this is what here, this is the definition of a this is functionally dependence. That is we can also write as here j of u, v, w divided by x, y, z is equals to 0. We can say that here if the Jacobin of UVW with respect to XYZ is equal to 0, then the function phi is known as functionally dependence. Let us take one more definition, functionally independent. That is here, the functions UVW of XYZ are said to be functionally independent if they are not dependent. That is, the Jacobin of UVW with respect to XYZ is not equals to 0. If Jacobin is equals to 0, then the function is said to be functionally, then the functions UVW are said to be functionally dependent, and if the Jacobin is not equals to 0, then they are said to be functionally independent. So let us take one note here. If J is not equals to 0, then the inverse of Jacobin, J inverse, exists and vice versa. That is here, if J is equals to 0, then we cannot find its inverse. If J is not equals to 0, then we can find its inverse J dash, and this is if J dash exists, then we can say that here the Jacobin J is not equals to 0.